All right, hello everyone. Welcome back to Physical Geology 1403. Today is lecture 3. We are learning about igneous rocks. Last time I gave you a breakdown of the rock cycle. So we went through igneous process and sedimentary process and metamorphic process as they all work together to make our planet through a whole bunch of other processes, right? Well, we're going to dive into each one of those parts. But today we are starting with igneous rocks, because I think that the easiest place to start on the rock cycle is with magma, and that's what we're talking about today. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Wait. Trying so hard to remember your name, brother. What's the first letter? Yes. G? Gavin. Yes. Hey, Gavin, would you get the door for me? Thank you very much. Okay. Okay, so while our lovely assistants are finishing up with preparing our example set today, so to speak, we're going to dive right in. But first, I'm going to ask you all if you have any questions. You've had 2 lectures thus far, your introduction and matter and minerals. Any questions about that content? Yes, sir?
Will we get time to complete this today?
Yes, you will have lab time today. You will have lab time today. And lab 2 isn't assigned until the next time we meet on Thursday. Okay? And like I said earlier in the class, I understand if lab 1 takes longer to finish because it is a longer lab. It's the longest lab. So there's a little bit of flexibility there. But again, I encourage you not to take too long on any one assignment, because the longer you take on one assignment, the further back it pushes the next one. And it's kind of a cascade effect until before you know it, 8 weeks are up and you're at the deadline and you still have 3 labs to do. Okay? So don't let it build up too long. Don't linger on it just because I say something like, I understand if you need extra time. Use that extra time. Don't waste it. Okay? Does your jacket match your dress, by the way? That's cool. I don't think I've ever seen a combo like that. That's neat. Way to coordinate. Okay. Any other questions? Nothing? All right, then. So I'm going to start off with this. Oh, no. Hold on. The speakers. I need to fix the speakers. There we go. Now let's start off with this. Or not. What's going on here? Okay. 3rd time's the charm, right? It's not, though. What is going on with this? It keeps defaulting to the laptop speakers. I don't want it to be on the laptop speakers. All right, we're watching. Hey, it did it. All right, let's try it one more time. Bear with me. Good. All right, what are we looking at? What do you see? Lava, right? There's a lot of lava. What's it doing? It's bubbling. It's spitting out. It's flowing. It's smoking. Right? In short, it is behaving as a... Lava is in what state? I've got a speaker next to my ear. You got to speak louder, man.
Flowing state?
Which is typically referred to as a... Huh? It's liquid, right? It is in a liquid state. What you can see here is lava in a liquid state. All right, there we go. All right, so magma is melted rock. Rock that has gotten so hot that the bonds keeping it as a solid substance have disassociated from each other, and it enters a liquid state. If I were to keep heating it, by the way, what would be the next state after that? No, that's if I were to cool it down. If I were to keep heating a liquid, what typically will happen?
It'll evaporate.
Yeah, well, it'll vaporize, right? It'll vaporize and enter a gaseous state, okay? So, what's happening here? Our mantle is made out of rock. Rock that is superheated. Rock that should, under any other circumstance, be in a melted state because of how hot it is. Yeah, just stick them back over there if you don't mind. And then you can go ahead and hand out those bowls to each person, but remember not to eat your M&Ms until we get to that part of the lecture, okay? All right, so mantle rises close to the surface as a solid rock. How does it become a liquid rock? We're going to learn that this week, okay? How it goes from solid to liquid, even though it was solid underground. Now, all lava and magma have what a multi-state components to them, okay? So there are liquid. What you see is mostly liquid. That's true. But did you see all of the gases coming off of it as well? There's a gaseous component to lava and magma. But there's also a solid component to lava and magma. Before I move on, I wanna test your brains just a little bit. In this liquid, why would there be any solids? See if any of you can figure this out before I teach you the concept.
It's not melted all the way.
Huh?
It's not melted all the way.
Boom! All right. It's not melted all the way. You ever heard the term melting point? Everything has a melting point. Even you have a melting point. We won't test it today. For legal reasons, I have to clarify I won't test it ever. But everything has a melting point. Like, whose Snickers bar did I mention last week was left on the dash, right? Someone over here, I think, I mentioned left their Snickers bar on the dash and it melted, right? The chocolate melted, and then the caramel melted. The nuts didn't melt. The nuts in that Snickers bar didn't melt. You haven't made it that hot, right? And they probably combust, right? But we haven't reached that point, okay? So everything has a melting point, and we'll dig into that concept later on. But that's an important thing to recognize right off the bat, is typically all three liquid, solid, and gas states are present in lava and magma. Now, this is what we're looking at happening in the mantle. We see the rise of hot material and the fall of cold material. I mentioned this briefly in our last lecture. Do you remember what cycle we called that? The rise of something hot and the fall of something cold? Convection. Thank you, Gavin. Okay, so when something is hot, it expands its volume but maintains its mass, lowering its... What's the metric that measures the relationship of mass and volume? Say it louder.
Weight.
Not weight. That's how mass and gravity interact. Okay, so you're thinking along that track, but what about mass and volume? The relationship of mass and volume is defined by a word, a metric. Density. Okay? When I expand the volume by increasing the heat of a substance, but maintain the same amount of mass, it lowers the density. When something is a lower density, you can take off your gloves unless you really want to keep wearing them. It's up to you guys. The substance in question will float, will rise, become more buoyant among the rest of the higher density material around it. This is what's happening in the mantle. Remember that. We'll bring it back up here in a moment, or in a little bit, okay? So, when a rock is beginning to melt, it is because you are giving it heat. Heat is a form of what?
Temperature.
Temperature is how we measure heat, but heat is a form of what? Energy. Thank you. All atoms are vibrating constantly. always shaking, always containing an incredible amount of energy that's causing them to vibrate. When two atoms bond with each other, it is because the vibrations of those atoms are not significant enough to prevent that bonding from happening. What if I were to add extra energy via heat to that system? What are my atoms going to do? They're going to vibrate harder and faster. And eventually, what's going to happen to that bond? It's going to break apart. Bonds disassociate from each other when you add energy to the equation. That energy, most commonly, being that heat, right? And that's why things melt. That Snickers bar, ice, and yes, rock. Add energy, increase the movement of those particles, and they can't stick together. And so you get disassociated liquids as a result. We had this previous crystalline framework. Now we have a loosey-goosey hodgepodge of atoms that kind of touch each other, kind of stick for a second, and then don't. They're still somewhat cohesive. It's a material that will generally stay together, but not form any significant bonds. And then if I increase the heat even more, what's going to happen? Those bonds or those atoms become so energized that they can't even stand being near each other. And so they start zinging all over the place, and that's what we call gases, right? When you're boiling water for your mac and cheese on the stove at night, right? You get the gas, the steam that starts rising off of it. It disperses quickly into the atmosphere. It'll condense on your stove or on whatever vent you've got above your stove. Sure, but that's a different process we'll talk about later. For now, we're focused on the vaporization. The water molecules that have become so superheated that they cannot stand being near each other and cannot bond with each other fly off into the atmosphere because of all the energy they possess. Okay? Same thing happens here. You can actually vaporize rock. Okay? You can get it so hot so fast that it will vaporize just like that. Okay? Now let's talk about the opposite. When I have a gas and I begin to take away its energy, what do we call that? When something's losing its energy, we call that. You just finished making your mac and cheese, but you can't eat it yet. It's too hot. You have to let it cool off, right? When our gas is cooling off, it's losing energy, and therefore will enter a state in which it can start to be more cohesive. Not quite forming bonds yet. We're back to being water, not steam. Then we take even more energy away, and it forms a crystalline framework. True for your Snickers bar, true for water, ice, true for rock. Okay? This is the process we're going to be talking about today, the process by which we make igneous rocks. You make igneous rocks by cooling magma or lava, depending on where it is. By the way, do you know what the difference between lava and magma is? Okay. Which one, besides Chris, someone else answer this, well, which one is above ground?
Magma is underground and lava is above ground.
Thank you. Jackson. I'm getting there. I'm getting there, folks. Okay? Yes, lava is above ground. Magma is below ground. Both are the same thing. We just give them different names depending on their situation. Okay. So now I'm going to start telling you the different ways that we differentiate igneous rocks from each other, now that we have an idea for how they form, the cooling of magma and lava. Intrusive igneous rocks are those which, making my microphone work, making sure my microphone is working. Intrusive igneous rocks are those which cool below the surface. They are typically characterized by a large crystal size, whereas extrusive igneous rocks are those that cool above the surface or very near the surface and are generally characterized by small crystal size. Let me show you an example. Large crystal size, intrusive igneous rock. Small crystal size, extrusive igneous rock. Can you tell the difference? Right. Pretty clear. Now, I'm going to tell you something very important. Please make note of this. Online students as well. Please. Intrusive and extrusive are not describing what the rock is made out of. They are not descriptions of composition. They are descriptions of cooling environment only. So basically what I've said is we can divide all igneous rocks into the ones that cool below ground and the ones that cool above ground. Great, cool. That's the first thing. That's the first factor you need to consider here. By the way, why would cooling below ground make larger crystals, do you suppose?
Because nothing's messing with it.
Ooh, nothing's messing with it? Let's dig into that. What do you mean nothing's messing with it?
Like there's no trees or people trying to clear the land above or whatever.
So you're talking about processes of weathering and even erosion, which would break a previously made rock down. I'm talking about the formation of that rock in the first place. Okay? You're just thinking too far ahead. Hold that thought for a week or two. Okay? While this magma is cooling down underground, why would it make large crystals while the lava that cools above or near the surface makes small ones? What's the difference there? Is it really just the difference between being above ground or underground? What's the difference between those two environments?
One's hotter and one's not that hot.
Say it louder.
One's hotter and one's not that hot.
Yell it.
One's hotter and one's not that hot.
All right, did we all catch that? Which environment is hotter?
Underground.
Underground. Which one's cooler? Above ground, right? Above the surface. Why would I get larger crystal sizes in a hotter environment?
I slipped over the wrong path.
Was that Siri trying to answer me?
Yeah, I think so.
Yeah. You don't know?
Because of pressure.
Not because of the pressure. Right now, this has to do with the heat.
Oh, yeah.
I like that you're thinking scientifically. It doesn't have to do with expansion, actually. It has to do with insulation. Ooh, right. Now we're getting it. What do I mean by insulation? Which one of these is going to lose heat faster?
The one above ground.
Mm-hmm. And the one that retains heat the longest?
The one above.
Mm-hmm. So what we can tell from this, logically, is that the longer my magma retains heat, the larger the crystals can grow. Here's a gross example for you. You have left your apple on the countertop. It's been there for a day. It's gotten kind of brown and gross. You don't really want to eat it, but you're too lazy to throw it away. So you leave it alone. A few days later, it starts to grow a bacterial colony all over it. It starts to get moldy. Yuck. Now you just don't want to touch it, and you can't really be bothered, so you leave it alone for another week. Is that bacterial colony going to get smaller or bigger? Bigger. It's going to get bigger. The more time something has, the larger it typically gets. That's how things grow, usually. Now, in the case of these rocks that are being made by the growth of minerals, the longer those minerals have to grow, the larger those crystals will get. And the eventual rock you get out of that, you'll be able to tell approximately how long it had to grow by how large the crystals are. Okay, so this is the difference between intrusive and extrusive rocks, igneous rocks. Okay, I'll talk more about that subject here in a minute. Now let's talk about compositions. So while intrusive and extrusive are not compositions and do not describe anything about composition, only cooling environment, now we are talking about compositions. First up, felsic. You can kind of break this down into that Greek word math I mentioned before, right? Where you've got fel, think feldspar, one of those minerals we talked about, and sic, think silica. Okay, so we're talking about a silica-rich igneous rock that has a lot of feldspar in it. You can think of it like that. Felsic compositions are very high in light silicates. Can someone remind me what the other word we used for light silicates are? I'll give you a hint. It starts with non, meaning it doesn't have something in it. No, we're only talking about silicates.
Non-silicates?
We're only talking about silicates. You can't really typically get non-silicates in volcanic rock. There's a few very niche ways, but we're not learning about that in this class. Yeah. Non-ferromagnesian, thank you. Meaning light silicates do not possess iron and magnesium as part of their chemical recipes, okay? Their chemical structures. So felsic igneous rocks are those that contain a very low percentage of ferromagnesian, dark silicates, and a very high percentage of non-ferromagnesian, light silicates. Perfect example is right here in front of me. Do you know what this is? Anyone want to take a stab?
Granite?
This is granite. Okay? Granite is a felsic igneous rock. Mostly feldspar and quartz, with a few dark silicates in there, which you can see. Now, this particular piece might be a little deceptive, because it looks like there's a whole bunch of dark minerals in there. But if you look closely, and I will pass this around the class, you'll notice that what at first appear to be dark silicates are actually clear gray quartz, which is a light silicate. There are definitely black colored minerals in there. Those are biotite micas. But it's the vast minority. Only about 5% of the volume of this rock is actually made out of dark silicates. The rest is light silicate. That is a felsic igneous rock. Yes?
Don't they use that in countertops?
Yes, granite is commonly used in countertops. Commonly used for other building materials as well. You are going to learn today, my friends, the difference between a granite and a fake. After today, you will never be ripped off by a countertop salesman. Yes. See, you're learning far more than just weird science in that class. You're learning practical skills. Someday, when you become a homeowner, fingers crossed, right? You'll never get ripped off by a countertop salesman because you'll know what real granite looks like. Yeah.
Is that copper and anthill casting?
No. So it does kind of look like an anthill casting, right? This copper is actually, this is what happens when you drop molten copper into just water, and it kind of swirls around and then instantly kind of vaporizes. Yeah. Or not vaporizes, the opposite. It condenses like that. Yep. Okay. Where was I? Oh, felsic. Right. Most of the continental crust is felsic in composition for reasons that we will learn as we move through the semester. Okay? Which means that it is full of light silicates, meaning it has a lower density. We already learned that continental crust has a lower density than ocean crust. And that is because ocean crust is made out of a different composition, mafic. Mafic composition, what do you think? Mostly light silicates or mostly dark silicates?
Mostly dark silicates.
You're all right. This is mostly dark silicates. That's what mafic means. You can think of Ma is magnesium and Fic for iron, okay? Mafic, okay? So this is made out of dominantly iron and magnesium rich dark silicates. This is a type of rock called basalt. B-A-S-A-L-T, very common mafic igneous rock. Most of the ocean crust is made out of this stuff, okay? Or a variation of it. In the same way that our felsic granite had a small percentage of dark silicates in it, this mafic igneous rock has a very small percentage of light silicates in it. Very hard to tell. Our eyes have a hard time picking dark and light colors apart from each other. Matter of fact, a lot of eyes do. That's why zebra coats work. You know, have you ever seen a herd of zebra? It's almost impossible to count how many of them there are because the black and white patterns keep intermeshing with each other and our eyes can't focus on any one object. Okay? Same thing is true for all the other predators that hunt zebras. That's why they have such an incredible evolutionary advantage by living in herds. Okay? Kind of broke into my 1404 lecture there for you. But there are definitely light silicates in here. It's just hard for us to see them in all of the dark silicates that exist in here. If I were to do a chemical breakdown of this, grind a section of this into powder, look at it through an X-ray machine, an XRF is what we call X-ray fluorescence, and then there's an XRD, X-ray diffraction machine. And those other machines, those sorts of machines can tell us what sort of atoms are present in here, what sort of minerals are present. We would be able to tell what percentage of this is light silicate. And it would be probably around 5%, just like with that granite, but in the opposite spectrum. Okay? So this is basalt, a mafic igneous rock. Then we've got intermediate. Now, where do you suppose intermediate falls on our scale? Not a rhetorical question. There it is. Where do you suppose intermediate falls? Right in the middle. Between what? Between what? What were the first two we talked about? Felsic and mafic. Intermediate rocks are between those. So if I've got about 25% or so light silicates, or 25% or so dark silicates, all the way up to the other side, so 25% to 25% of one or the other, we'll typically refer to it as an intermediate igneous rock. There's a little bit of variation there depending on the rock, but generally speaking, that's where we draw the line. Okay? So, look at this. It appears to have approximately equal proportions of light and dark minerals in there, right? Intermediate. This is a type of rock called diorite, an intermediate igneous rock. Diorite is one of the rocks that is most commonly confused with granite. If anyone ever tries to sell you a countertop that looks like that. Okay, so funny story actually. I keep bringing up countertops because it's a real thing. When I bought my current house, the builder said, all right, you've got options for what you want your counters to be made out of, how you want your cupboards painted, stuff like that. And so we went into their show office and they showed us all the stuff and they're like, okay, these are all your granite options. And I walked around and they had about 20 options and I made it to the end and I said, well, only 2 of these are actually granite, so I think I'll go with that one. And they're like, what are you talking about? And I said, well, I'm a geologist, and this is what granite has. You know, it has these proportions of these things. It has this much quartz, which is what makes it so hard, you know, great for a building material and all of that. And they're like, okay, sure, yeah, you can have that one. Just a funny little flex you can have if you know your stuff, right? Okay, so that is an intermediate igneous rock. But why does it matter, by the way? Why does it matter if you have granite or not? Granite, one of the things that makes granite so good for the purposes we use it is the proportion of quartz that it has. What have we learned about quartz so far in our minerals talk and in our minerals lab? Can anyone tell me what the hardness of quartz is? It's definitely harder than glass. It's harder than just about most of the other minerals. It's a 7 out of 10 on the hardness scale, right? Which means that it's harder than anything else in that granite. If someone's trying to pawn off rock to build my house or my countertop out of, and it doesn't have any quartz in it, it's not going to be as strong as true granite, right? So that's why it's important to nitpick that a little bit. If I was going to build my house out of what I thought was granite and it couldn't actually stand up the way that true granite could, that would be a problem, right? So that's why it's important to know. Okay, ultramafic. Ultramafic is what you get deep underground. So mafic igneous rocks are what make our oceanic crust, right? We do get them on continents, but it's what makes up our oceanic crust. Deep, deep, deep in the mantle, we get ultramafic. And you've actually already seen an ultramafic igneous rock right here. I passed it around the other day. That green stuff, that's olivine. The black stuff, that's pyroxene. This is an ultramafic igneous rock. 0 light silicates present here. Only dark silicates. Because it happens, it's formed so deep underground. Okay?
There's a quartz in that?
No. No, there's no quartz in that. Quartz is among the last minerals that form in the light silicate series. We'll talk about that today. That's actually part of the experiment with the M&Ms. Reminder, don't eat those, right? By the way, did we run out of yellow M&Ms? Or is there still just a few left? All right, I'm gonna have to get more M&Ms. You can order specific colors of M&Ms from the M&M store, but it's ridiculously expensive as it turns out. So what I did was a few years ago, I bought a whole bunch of buckets of M&Ms from Sam's Club, and my wife and I stayed up like 4 nights straight sorting out all the colors for this experiment. So maybe this time I'll just order yellow. I don't know. Yeah. Yes, you may. Right? And before you all start making a fuss that I said, wait, you did that a few years ago and you're still giving us these M&Ms? Yeah. Do you have any idea how long those M&Ms were on a warehouse shelf before they went to the store that I bought them at? Right? The candy you eat is typically already a few years old. Okay? They manufacture it way far in advance. Okay. Especially considering, interesting fun fact, gosh darn it, I warned you that I would keep going on tangents. Okay? M&Ms were actually developed for the military. Did you guys know that? That candy coating, it keeps them from melting. So whenever military members would be in really hot places and they needed some form of candy, the military needed to give them some sort of candy for morale reasons. They needed something that wouldn't leak chocolate all over the place. And so they developed M&Ms with a hard kind of coating to keep them from melting all over the place. And now we eat them. So military hardware, yay. All right. Now, let's talk about silica. Silica is important. Why? What did we learn about silica the other week? In as much as it relates to magmas and lavas. These minerals we just talked about, we call them silicates. Why? What are they built around? Whatever you're saying, say it louder, brother. Yeah, they form in magma or lava, but they form around what? There is a single structure that must form before the silicate mineral can be built around it. It is a silicon tetrahedron. There it is. A silicon tetrahedron. 1 silicon, 4 oxygens, right? And then metals with negative charges will attach to that, or positive charges, excuse me, will attach to that, right? And that's where you start to form your silicate minerals based around that tetrahedron. So silicon, already really important to this process. But now we're going to discuss a way that it furthers the plot, so to speak, even more, okay? Because of how much silica we have on our planet, there is a high percentage of silicate minerals, making silicate-based rocks, igneous rocks being the foremost example of that, okay? Igneous rocks are silicates, and we have a lot of igneous rocks on Earth, especially at the surface. There is an inverse relationship between the amount of silica that a rock has and the amount of dark silicates, or excuse me, the amount of ferromagnesium, I should put it this way, minerals present there, okay? There is more silica in light silicates than there are in dark silicates in general. So if I have a composition that is mafic, aka heavy in the dark silicates, it will also have proportionally less silica in it than, say, a light silicate would. So let's use pyroxene for an example, okay? Or, excuse me, let's go with a rock, not a mineral. So basalt, which is rich in pyroxenes and olivines and amphiboles, those dark silicates, is going to be high in iron and magnesium, but low in free silica. Whereas a feldspar is going to be very low, even non-existent. Let's go with a granite, not a feldspar, okay? It's going to be very low to non-existent dark silicates, but very high in silica. There's an inverse relationship here having to do with the proportions, and that's dictated by your composition. So now, here's another thing that silica does. Silica will affect the viscosity of your liquid. Someone explain viscosity to me. First of all, it's a really fun word to say, viscosity. You got to say it like you're a British royalty. It makes it sound that much better. Someone describe what viscosity is.
How easy like the liquid would flow?
Precisely. How easily does it flow? Specifically, its resistance to flow. I have here two liquids. One is less viscous and one is more viscous. If a material is less viscous, that means it flows easily. If a material is more viscous, it flows poorly. You ready? Here we go. Oh, it's a close one. It's closing. Oh, man. Oh, who's going to win this? Is it the rabbit or the hare? Do you guys get that reference? Are Aesop's fables still a thing?
What is that, honey?
No, this is corn syrup. Next time you eat a gummy snack, think that this is what you're putting in your body, by the way. Yeah. That's what corn syrup looks like. Delicious. Look at that. Ah, it's definitely a liquid. Ooh, yeah. Oh, yeah. Yummy. Okay. It's flowing. It sure is flowing. But it's not like this, is it? Which one has a higher viscosity? AKA more resistance to flow. The corn syrup. It's going to take about a week for all of that to reach the bottom, by the way. Okay? So, how does this relate to magma? The more silica that is present in magma, I'm going to put these down here so that the camera can see the PowerPoint better. The more silica that is present in magma, the higher the viscosity, aka resistance to flow. So if I have a lava that is low in silica, which would mean it's what composition? Remember that inverse relationship. Low in silica means high in iron and magnesium, which makes it what composition? Someone take a stab. Huh?
Can you repeat the question?
If a substance is low in iron and magnesium, but high in silica, what composition is it?
Mafic?
That's the other way. Mafic is high in iron and magnesium and low in silica. So high in silica and low in iron and magnesium would be felsic, okay? So if I have something that is high in iron and magnesium and low in silica, it is what again, Jackson? No, Mafic. The one that you said was Mafic, right? Faith, I think you said the felsic one, right? Oh, someone over here said it, I thought. I want to give credit to the right person. I wasn't looking there at the time, okay? Okay, so this is what a fast-flowing mafic lava looks like. It's going pretty quickly for melted rock. You wouldn't expect melted rock to move that fast. It can go faster. Stuff can go 35 kilometers an hour. It's like, you better be on a bike at least. You're not outrunning that, right? It can go really fast. That is a low viscosity lava, okay? What about a felsic, high silica lava? Look how fast that one's going. What do you think? Are they equivalent? No, that's the corn syrup of lavas, right? You can actually see the outer surface is actually forming like solid material on the outside. It's going so slowly that it's actually cooling off as it pushes forward, right? which will probably even slow it down more. All right, now I'm going to play a video for you next. You're not going to see a whole lot of movement, but you're going to hear something. You're going to hear wind, first of all. Listen past the wind. It wasn't really possible to remove the sound of the wind. But what you're listening for is the sound beyond the wind, okay? Try and find out what that sounds like. Tell me after the video is done. Breaking glass. Raise your hand if you think it sounded like breaking glass.
Sounds like Legos.
Okay, raise your hand if you think it sounded like Legos. Wait, you're changing from breaking glass to Legos?
It sounded like both, kind of. I think it sounded like.
Hold on, we're talking about just like Legos? Like that's the sound of a Lego, or like you're breaking Legos?
No, like Legos, like falling. No, like,
Okay, Legos
like
falling.
tumbling.
Like
I think
dropping
it
the
sounds like
Lego.
glass or land.
You think it sounds like breaking glass? You think it sounds like tumbling Legos? Any other things you should put out there? Who thinks it sounds like a whale? No? Okay. It is, in fact, breaking glass. That's what you're sounding like. And by the way, it's way louder in person. In person, this sounds like 1,000 dinner plates being shattered all at the same time without stopping. It's deafening. Okay? The video doesn't really do it justice. Why would a lava flow like this sound like breaking glass? What's happening on the outside of this lava flow? What?
It's cooling.
It's cooled off. It's formed a solid substance, right?
Oh.
What happens?
It starts to cool, so it's every time as it's coming down, it's like breaking.
The outer surface of our lava flow is cooling off. As it cools off, the lava behind it is still shoving it forward, and it breaks. But why does it sound like glass? What happens when you cool lava quickly?
Obsidian.
You get glass. When you take a lava and you cool it like this, via very cold wind or in the water especially, you make glass. We call this obsidian. Have you heard that word before? And no, you cannot get obsidian and make a portal. I know. Breaking hearts out here. Yes?
Don't they make arrowheads out of obsidian?
Yeah. Yes, you may. All right. It took me a second to remember what that meant. Thank you for teaching me that. Yeah?
Trying to break it.
Huh? Is this hard to break? Well, it's glass, so I could break it.
Trying to break it.
Yeah, no, please don't try to break my glass. Okay? So, look at this though. Clearly glass, right? Oh, it's green, isn't it? We'll talk about that in just a moment. But when you quench, aka very quickly cool off a lava, it doesn't matter what the composition is, it will make glass. I've actually flash melted basalt and then flash cooled it, and I went from a chunk of a black rock like that basalt I handed you earlier to a clear, crystal clear green bead of glass. It doesn't look like the original thing. It still has all of the same material though. It's just formed glass instead. This is how we make the glass around us, people. We melt rock and then cool it quickly into the shapes that we want it to be. Yeah?
Could it also be sand?
Yes, so sand is made out of quartz typically. Quartz makes the clearest glass, which is what we usually make all this stuff out of. Okay? Most glass that you see, especially the clear stuff, is going to be made out of quartz sand, the purest quartz sand we can get. If you want it to have various colors, like for stained glass, you add stuff in, like other minerals, to give it that changing color. Yeah, Gavin.
Crystal clear green.
Oh, was it in your kit?
Yeah.
No. That's a different thing, which I won't tell you. It's a part of Lab 1. You got to figure that out for yourself, unless you have a guess, and then I'll tell you if you're right or wrong. Okay? Okay, let's go back to this for a second. I'm going to pass this around. Let's hear some observations. We already got one. It's green. Why is it green? Huh? Say it louder. The minerals, yes. What minerals specifically? The minerals that were in it before it got melted, right? Whatever was in it before is going to change its color when it becomes glass. Perfect. For example, check that obsidian out. You tell me what colors you see in that one. Aaliyah, right? Yeah. Do you see black in there?
Yeah.
And then those red stripes, right? We call this mahogany obsidian. It's black and red. Yeah, I'll show you a picture here in a few slides that shows you how many different varieties of obsidian there are. There are tons. Why? Because it is glass that gets its color off of whatever minerals were in the rock when it melted. And therefore, whatever was in it, when it flashed, instantly solidified into glass in whatever circumstance that happened. What else do we observe about that piece I'm handing around, by the way? I'll hand this around going that way. What do we see in that, Gavin? Besides the color being green. Ripples. Okay, what those ripples are is actually the conchoidal fracture that we learned about in our last lecture. Okay, both quartz and glass do not break along any forms of cleavage. They break in that ripply sort of shape. We call that conchoidal fracture. Remind me what your naming is again, brother? Onyx. That's right. I gotta remember. Onyx. Onyx, what do you observe in that?
There's like little dots inside.
What are the dots? What do they appear to be? Say it. I see your face trying to say it.
Water.
That's not water. I saw your lips were starting to form that word though. The one I'm looking for. Bubbles! These bubbles, right? They are in fact bubbles in that glass. Why are there bubbles in that glass?
Because the air didn't have time to escape.
Ha-ha! It cooled too quickly. That's why it made glass. As gases were forming in this lava, like I mentioned earlier that they do, they could not escape. It cooled too quick and those bubbles get trapped in the glass. And guess what? Those bubbles still contain the gas mixture from when it was a lava. There's a whole bunch of scientists that all they do is study the bubbles trapped in volcanic glass to get information about the chemistry of the lava that existed at that time. Fascinating. Okay? All right. Let's talk about igneous textures. This is going to be your next little friend in helping you identify igneous rocks from each other. So we've learned cooling environment, intrusive and extrusive. We've learned composition, felsic, mafic, intermediate, ultramafic. Now we're moving on to the next bit. That is texture. The texture of an igneous rock is generally described as the size, shape, and arrangement of crystals in your rock, the minerals that are in your rock. We've already talked a little bit about how each one of these things is important. Now let's put this all together. The size of my minerals can help dictate how quickly it cooled. We discussed this. Let's dive into it a little bit more. If my mineral cools slowly, will I have large or small crystals? Let me put it this way. How large are the crystals in the glass? Jackson, you've got it right now. How large are the crystals that you see in there?
Not very big.
Do you see any?
No.
No, there are no crystals in that. Whereas with my granite, how many crystals were in here? A lot. And how easy to see? Easy. That was quenched. In a moment, went from a liquid to a solid state, no time at all for any crystals to grow. This one probably took millions of years to cool down. That is the difference, my friends. The size of the crystal is dependent upon how long those crystals had to grow. The faster it cooled, the smaller the crystals. Then there's the amount of silica, right? The amount of silica can be a factor because A, it'll provide the tetrahedrons, okay? This is the primary reason. The more silicas there are, the more tetrahedrons that can form as, think of them as the seeds of the crystals that are growing. You cannot form a silicate, either light or dark, without a silicate tetrahedron. Yes, you may, okay? Without those, you don't form them. So the more silicas there are, the more tetrahedrons can grow, and therefore the more minerals you can get in the first place. Okay? And then there's the amount of dissolved gas as well. Excuse me. The bubbles that you saw in that obsidian, and get these out of your way, Remy. The more bubbles that you see in that obsidian, or in any other rock, the more voids or empty spaces are going to be present in the rock after it cools off, right? So while this granite has 0 voids, 0 holes from bubbles, I could end up with something like that. That's filled with holes. All those holes are left by gases that formed in this as it was cooling. We'll talk about this rock in a little bit. And then you've got your volcanic glass, which was quenched, just like that, okay? And you end up with obsidian of one form or another, okay? So let's talk about all these different textures. And by the way, you are going to need to become familiar with these for Lab 2, which you will get on Thursday, the next time we meet, okay? The first texture is aphanitic. That's how you pronounce that. I'm so curious about what you're doing right now. Why are you knocking on it? Just because? Just to see if it would make a noise? Well, now I gotta know. I didn't hear anything. Did you hear anything? All right. Okay. Experimentation. It was fun. Okay. Aphanitic is the first texture. Aphanitic igneous rocks have tiny crystal sizes. Small enough that you pretty much will need a microscope, or at the very least a magnifying glass, to see most of them. Okay? These are generalizations. As long as most of the minerals, the vast majority of them, are aphanitic, we call the rock aphanitic. Okay? So aphanitic, very, very, very small crystal sizes. Okay? You need some sort of assistance to, some sort of visual assistance to see them. Also very common in aphanitic igneous rocks to see that they are filled with those bubbles we mentioned earlier. Except now I'm going to teach you the word for those bubbles. You ready? They are called vesicles. Vesicles. That's this word right here, V-E-S-I-C. And in this case, vesicular, U-L-A-R. Vesicular is the description. Vesicles are the holes, the bubbles themselves. Okay? So if my aphanitic igneous rock has vesicles in it, I would say it is an aphanitic vesicular igneous rock. Okay? That basalt I passed around earlier had a few holes in it. I would describe it as a vesicular aphanitic igneous rock. Okay? Here's a cool picture right here. This is basalt, just like what I passed around earlier. What do you notice about the degree of vesicularization? There's a long, fancy word for you. The degree of the quantity of vesicles in this rock as you go up. What do you notice? What's the pattern here?
Increases.
The quantity of bubbles, aka vesicles, increases the closer we get to the top of this flow. Imagine this as a lava flow. It's flowing off that way. This is closer towards the middle. This is closer to the top. Which is cooling off faster? The top, right? The outer surface of my lava flow is going to cool off the fastest. And so as my gases are forming down here, where it is still hot and liquidy, they're going to migrate upwards until what? What happens when they reach this much gummier, much more viscous cooling off liquid?
They expand.
I mean, yeah, there will be some expansion, but more than anything, they get stuck. They cannot move upward anymore and they get trapped there, and so the rock cools off. And so you get a lot more bubbles up here near the surface of cooling than you did down here in the middle where they were able to easily escape upward from. Okay, so that's the pattern we're seeing here. All right, so that's aphanitic igneous texture. Phaneritic igneous texture is where you have large, easily seen crystals corresponding to what kind of cooling? Long or short cooling? Long. Longer the cooling, larger the crystals, right? Okay, so when a rock has that, we say it has a phaneritic igneous texture. And here I have a couple of examples. Here we have a felsic phaneritic igneous rock, granite. Here we have a mafic phaneritic igneous rock. This one's called gabbro. I'll pass around a piece of it in a bit. And here we have an intermediate phaneritic igneous rock. We already met this one, diorite. Okay, large crystals easily seen. Then we've got porphyritic, which is a combination of the two, aphanitic plus phaneritic. How could that possibly happen? How can I get an igneous rock that has both microscopic crystals and large, easily seen ones?
If it was underground but closer to the surface?
Think of that over time versus in one location. You've got the right idea, though. Where did it start?
Oh, it started down low, but it made its way up.
There you go. That's one circumstance. One way that you can get a porphyritic igneous rock is if you started deep and therefore you were forming crystals slowly over time, and you get a bunch of them that form, and then all of a sudden it gets shoved up to the surface and the rest of your magma cools off quickly, making the microscopic crystals. That is one way. Can anyone think of the second way?
It starts like closer to the surface and then goes down.
Not quite. I don't know what you're doing here. Are you working through it in your head? Yeah, that's good. Angelina, any ideas? No? Any ideas?
Wasn't I close?
No. You're thinking through your previous idea in the reverse. It doesn't quite work that way.
Does it like go downhill?
Not downhill. Tell you what, think of your original idea, but not in terms of location. Think of it in terms of temperature. How about that?
Oh, the cooling of the...
Whereas before we formed this through cooling, is there a way we could perhaps form something like this through heating?
Oh, like underground near a volcano?
I mean, again, you're thinking of terms of location. Think of it in terms of temperature. What if I took that granite and I melted it, but not all of it? What if I reached a melting point in which 3 out of the 4 minerals melted, but not the 4th one, and never quite got that hot? I would still have, in my magma, large crystals of that unmelted mineral floating around in the magma made by the melted other 3. It got partially remelted and then crystallized again. That's the second way I can get this texture. So the first way, partially cooled off underground over a long period of time, making the large crystals, and then got shoved up close to the surface, cooled off quicker and formed the microscopic ones. Or I have a previous rock that got partially melted, leaving behind large crystals from the original rock, and then it got cooled off again, making the microscopic crystals. Those are the 2 ways that you can get a porphyritic igneous rock texture. I'm going to start this one down that way. Careful, it's heavier than the other ones. Okay. Then, of course, there's our glassy texture. We're well familiar with this. I promised you this slide would come up, okay? The various forms of obsidian, okay? So you've got blue sheen obsidian, which is exactly what it sounds like. Fire obsidian, which is gorgeous, usually a combination of purples and greens. It's awesome. Rainbow obsidian, golden sheen obsidian, snowflake obsidian, mahogany. I already showed you mahogany obsidian. I don't know if did I pass around the mahogany obsidian yet? I think I did, right? And then this ended with you, right? Okay. So this was the mahogany obsidian, okay? Let me put up close to the camera again so that folks online can see. Let it focus in on that for a second. Okay. Now, there are other different types of volcanic glass that can form. I lived in Hawaii for 3 years, and I found several different types of obsidian. So whenever the volcanoes in Hawaii spit out their lava, I don't say erupt. Volcanoes in Hawaii don't really erupt explosively at all. We'll talk about the different types of volcanic eruptions on Thursday. But Hawaii more or less just spits, okay? It spits lava out. And a lot of volcanoes are close enough to the coast that the little droplets of lava will fall down into the ocean. When they do, they instantly crystallize, making teardrop-shaped obsidian pieces. They call those Pele's tears, because Pele is the Hawaiian goddess of fire and creation. Okay? So they call little teardrop-shaped ones, they call them Pele's tears. But every now and then, you'll get a string of lava that gets spat out, okay, and falls in the ocean and instantly condenses, instantly solidifies into a string shape instead of a teardrop. And those string shapes, they get washed up on the beach, and they call this Pele's hair. It has the thickness and consistency of hair, but they are strands of glass. Okay, so they call it Pele's hair, and it just washes up on the beach. So you can find varieties of obsidian in many different shapes and forms and all of that. Okay, but it's all glass, all formed through the instant quenching of lava. And that's a glassy texture. Okay. Then you've got pyroclastic texture. Pyroclastic is the one exception to the rule that I told you before. I told you before that all igneous rocks are formed through the cooling of magma or lava, correct? I did tell you this. There is only one exception, pyroclastic rocks. They generally are not formed through the cooling of lava or magma, or at least they don't have to be. Some of them are, but they don't have to be. Pyroclastic igneous rocks are formed through the process of a volcanic eruption. Because they're in the volcanic process, we still count them as igneous rocks. They, at some times, look like sedimentary rocks, but they are still igneous rocks by our definition. Okay? So what does this mean? Anything that was made from the ash of a volcanic eruption, anything that was made from the debris thrown off of the volcano in a volcanic eruption, okay? Any chunk of lava that flew through the air, cooled off in the air, and then landed somewhere else is pyroclastic, okay? So here's an example right here, okay? This is a volcanic breccia, which is essentially a whole bunch of ash and shattered rock from a volcanic eruption that got piled on top of itself, welded together, and made a new rock, okay? Camera, stick with me there. There we go. Volcanic breccia. None of the fragments that you see in that rock are crystalline. They're all jagged, chunky, shattered pieces of previously existing rocks, destroyed in the volcanic eruption, and then smashed together and welded together with that super hot ash that fell from the eruption. We'll talk more about how that stuff forms when we discuss volcanoes next time. Okay, and the final texture is pegmatitic, okay? So a pegmatite is a structure that will form at the very end of a magma chamber's life. A magma chamber is a body of magma that exists underground. As they cool off, their chemistry changes. This is something called Bowen's reaction series, which we will discuss here in the next few slides. As its chemistry changes, the very last thing that it forms is a pegmatite. And pegmatites have truly massive crystal sizes. The largest feldspar crystal in the world was found in a pegmatite, and it's the size of a 2-story house. This is a cave in the Nika mine in Mexico, a pegmatite cave, and yes, that is a person right there, if you didn't notice him, in that cave. One of my life goals is to go into that cave. It's in Mexico, the Nika mine in Mexico. It's closed to the public right now. You need a special permit to go in. It used to be open, but then people started destroying crystals to take chunks of them home, as stupid people are wont to do. Yeah? Which one? Oh, that is the porphyritic igneous rock, the porphyritic texture. Yep. My uncle, my great uncle, was a geologist. He worked during the 80s and 90s as a geologist, and back then this was open. So he has a picture of himself right there in that cave. But you need special permission to go in now. Anyways, that is a pegmatite. Pegmatites are extremely valuable because they are made out of the rarest elements. Okay? The most expensive ones typically form in pegmatites. I'll tell you about why when we learn about Bowen's reaction series. Just remember, that is the case. It'll come up later. Okay, so those are your igneous textures. Any questions about igneous textures?
I was Googling the mine.
Oh, yeah. Okay. Now let's talk about the process by which we figure out what your igneous rocks are. Okay? So, we get valuable information by studying the texture and the cooling environment and the composition, and we can get information about where the lavas came from, what conditions were like when they formed, how deep underground did they come from, how old was the magma chamber when the lava got pushed to the surface. We can get all sorts of cool information like that. But as far as figuring out what your actual rock is called, you can take all of these factors together. Okay? So you can take your texture and your composition, and you can make more or less a flowchart, a grid, along which you can pretty accurately describe what you're looking at and find the answer. For example, right here, felsic, intermediate, mafic. Porphyritic, aphanitic, phaneritic. If I were to tell you, give me the name of a common phaneritic felsic igneous rock, what could you tell me? Granite. You win! Now give me the name of a common aphanitic mafic igneous rock. Huh? Basalt. You win! Great! It's pretty easy. Okay? You got your compositions, you got your textures. If you can figure that out, you're pretty well set. There are a few other things that you'll be finding in the lab, but all of them are peripheral to the main ideas here. Okay? Like, what's the general ratio of dark silicates present in this rock? It's about 5%. Okay, cool. Even more evidence it's felsic that you're looking at. Stuff like that, okay? For the most part, it comes down to your composition and your texture. So now let's talk about some of these most common igneous rocks. Granite. Like I mentioned before, granite is a very common building material. It's very important to be able to determine what is granite and what is not. Again, the big factor there is granite has a high percentage of quartz. That's not to say other igneous rocks don't, it's just that granite has the most, making it the strongest because quartz is the highest on the Mohs scale of all the rocks present here. Okay? Then you've got rhyolite. Now, rhyolite is the aphanitic version of granite. What do I mean by that? Both granite and rhyolite can come from the same magma, and often do. The difference is this one, intrusive. This one, extrusive. Same chemical composition, but cooled below ground and cooled above ground. if I were to take these, if I knew that these came from the same magma, if they were in the same location, I could take these and put them in a machine and see that they had the same composition, just different cooling histories. Okay? So I'll pass these around. Rhyolite flows on the surface, by the way, very rare. Oh my goodness. Did I not give you all a bucket of orange? Yes, there are orange M&Ms that need to go in there too. I did not. All right, we'll pass this down and everyone can count out your own. Let's start down here, okay? You'll need 30 oranges in there. 30. Yeah. Actually, because you guys probably don't all want to touch the M&Ms, do you? Can I get a volunteer to help hand these out? All right, go ahead and put on some more gloves and then count out 30 oranges. That was my bad. I must have run out of the old orange container and not taken one out from the back. Okay, I'm going to keep talking while they do that. All right, I wondered why it went so fast when you all did it. I was like, oh man, there's 4 of them. It went so quick. Yeah, yes you may. All right. Why are rhyolite flows rare on the surface, by the way? Any ideas?
You said why are they barely on the surface?
Because they're formed deep underground.
No. Rhyolite forms at or near the surface. It is aphanitic. It is extrusive. But why is it rare to find a flow on the surface? Huh? What does it contain? Here we go. Let's build on that. What does it contain? It doesn't have glassy voids. There's a high quantity of something. Remember, what composition is it? Composition of granite and rhyolite is high in yes, silica. It's high in silica, which means how easily does it flow?
It's not good.
Yeah, it's high in viscosity. It is highly viscous. It's the corn syrup, okay? It's not going to flow easily. So how far is it going to make it when it gets to the surface? Not far. Boom, bada boom, logic, logic, logic. Not very many rhyolite flows at the surface. Okay? Does that make sense? Great. Obsidian. We already talked about obsidian. I have it with the felsic igneous rocks. Why? Because it's mostly silica and oxygen. Okay? With other things in there, it may have come from a basalt at one point, but it's not basalt anymore. It is now felsic because it's made out of glass. Okay? Pumice. Who's heard of pumice before? You ever heard of pumice stone? You ever been to a spa? How many of you have been to a spa? Did they ever use pumice stone or have pumice stone available to you? What is it? It is an igneous rock. Yeah, pumice is an igneous rock. Pumice is actually glass. This is essentially obsidian that's filled with so many holes that it will float on water. Pumice is the only rock that will float on water because a lot of its volume is just air because of all the holes. You can think of pumice as the foam that pops out of your volcano right after an eruption begins. It's blasted out. It's just filled with so much air from the gases in that magma chamber that it instantly cools off and makes this hole-filled chunk of glass. And because it's made out of sharp pieces of glass, we can use it to, scrub stuff off our skin. That's why pumice stone is popular in spas. Okay? Pumice. Felsic igneous rock. Highly vesicular. Let's move on to intermediate. Andesite. That's the rhyolite, by the way. Andesite, right here. Andesite is the aphanitic intermediate igneous rock. The extrusive version of diorite. You remember this guy? This is the extrusive version of that. Approximately equal proportions of light and dark silicates, but with a crystal size smaller than that which you can see without a microscope. Cool? By the way, andesite. Andesite. Where does that name come from? I don't expect you to know, so I'll just tell you. There is a mountain range in South America called the Andes. You've heard of this? The Andes in South America, have you heard of them? The Andes mountain range? No? The Andes are mostly made out of this. It was characterized there. And therefore, it got the name andesite after the mountain range where it was studied and characterized from. Okay? Andesite. And then, of course, there is the intrusive phaneritic version of andesite, diorite, which we already learned and talked about, but I'll pass it around with the andesite actually so you can compare them. Okay? Some people call it salt and pepper rock. Some people call it zebra stone. Its actual name is diorite. Okay? And again, the andesite and the diorite are going to be the same chemical balance, just different cooling histories. Now let's talk about the mafic. We've already discussed this guy right here, basalt. He's come up a lot. Aphanitic texture. Mafic composition. Extrusive cooling environment. Are you following along how we start to narrow down the differences between these by these characteristics? Right? They all fit in that grid, in that matrix. Okay? Somewhere. You just got to find the ways to describe them. Okay? This is the most common extrusive igneous rock, by the way. Very, very common. Why is it the most common? I told you that something on our planet is mostly made out of this. What was it?
Ocean.
The ocean crust. And how much of our planet's surface is ocean?
70%.
A little over 70%. Logically found that answer, right? This must be the most common extrusive igneous rock. Now, but what if I had basalt composition, but phaneritic in texture? That, my friends, gives me gabbro. This one right here. Large crystal size. Okay? Mafic composition. Intrusive cooling history. Same composition here, different cooling histories. Gabbro. Also makes for a pretty good building material. You will often see people having diorite or gabbro countertops after being told that it's granite. Okay? Then we've got our pyroclastic. Yes, of course. Okay, then you've got your pyroclastic igneous rocks. The ones formed during the volcanic eruption. I already passed around that, yes, I did, right here. Pass this around, okay? The volcanic breccia. I'll pass around another one right here, a couple more actually, okay? This is welded tuff, T-U-F-F, tuff. This is what happens when blazing hot, what's up?
Can't find the lid.
Oh, okay. It migrated. Okay? This is what happens when that blazing hot, incandescent ash from a volcanic eruption sifts to the ground and then welds together. Okay? It gets essentially melted together and makes its own rock that we call welded tuff. That's volcanic ash that has sealed itself together and made a new rock. And then you've got these things called lava bombs, which we will discuss in far more detail on Thursday, but are essentially chunks of debris, semi-melted debris from the volcanic eruption that get thrown through the air, and as they go through the air, they take on this aerodynamic, almost teardrop shape. We call these lava bombs. Okay? These are both pyroclastic. Any questions about any of those rocks? clear some more space for you, Remy. Okay. Now let's talk about where magma comes from. I promised you we'd get here at the beginning of the lecture, okay? So as I mentioned, the mantle is solid, but we have to go from solid mantle to liquid at some point for us to get lava at the surface, right? Right? Yes. All right, good. Are we doing okay? Are we keeping up? Should I tell you a joke to wake you up?
Yes.
Yeah? All right. So a frog calls up his fortune teller, wants to know his future. Fortune teller stares into a crystal ball and says, I see a beautiful girl in your future. And the frog's like, oh my gosh, that's so exciting. Where do I meet her? At the club, at school, or what? Fortune teller says, no, she's going to be totally fascinated with you, by the way. She's going to think you're the coolest, most interesting thing she's ever seen. And the frog's like, well, tell me where I meet her. I got to know where I meet her. I got to know where I meet this girl. And the fortune teller says, biology lab. Yeah, there you go. All right, we getting it? Did everyone get that one? Okay. No, that wasn't a good one.
We should dissect it.
We should dissect a frog. That's not in the bounds of my classroom. You got to go upstairs for that one. I think they also dissect sharks up there in their lab.
What class was that?
Biology. I'm not sure which one. I don't know. Remember if it's biology 1 or 2. I have seen them dissect sharks though. Okay. Where was I? Origin of magma. How do we get to make liquid magma near the surface so that it can put liquid lava at the surface? Something has to happen. Well, there's this thing called the geothermal gradient. The geothermal gradient is the rate at which heat increases the deeper you go underground. Let me give you an example. This is the deepest mine in the world. This is the Tautona mine in South Africa. Okay? That's what it looks like at the surface. Field trip, anyone?
Yes.
I got a yes and I got a definite no. You don't like going below ground? Are you claustrophobic? Gotcha. Gotcha. Have I told you that I cave? Yeah, I'm a caving guide. Yeah.
Do you go in those little tight spaces?
Mm-hmm. I actually, so my YouTube channel where I post these lecture videos, Heart Rock Geology, I have videos of my caving trips on there. Yeah, squeezing through tunnels that go like, they're about that big around for about 40 feet. Yeah, it's really fun. I enjoy it. I go a couple times a year. Okay, so this is what a cross-section of that mine looks like. Now this map was drawn in, I want to say 2015, so it's actually gone even deeper since then. But at that point in time, it was 3.6 kilometers deep. It is so hot at the bottom of that mine that the workers that go down there have to take turns in refrigerators so they don't die of heat stroke. It's actually one of the places in the world where they are pushing the most for robotic workers, so that they don't have to risk any people's lives being anywhere that hot for that long. Okay? It's also very inefficient to have to spend 30 minutes in a refrigerator every time you go into work, right? Or every hour or so, right? So robot workers, they're exploring for that. Okay, so but why does it get hotter the deeper you go underground?
Because you're closer to the core.
You're getting closer to the core. Now, 3.6 kilometers is nowhere near how close to the core it gets, right? It's like if I put a single piece of paper on above the ceiling tiles here, and the ceiling tiles, the thickness of the ceiling tiles was the thickness of our crust. That's the thickness of that piece of paper is how close we'd get to the core if the core was the surface of our floor. Okay? It's extremely, extremely small. It's the width of my fingernail if the length of a football field was to the core, right? It's ridiculously small amount of distance, but even then, it's so hot that people can barely survive. Okay? So the closer we get to the core, the hotter it gets. Good. This is the geothermal gradient, the rate at which heat increases the deeper you go underground. Here is a graphical representation of the geothermal gradient. This hockey stick is the gradient. As you can see, Heat increases relatively slowly at first, and then it picks up, and then it picks up, and then it kind of tapers off. At about 1500 degrees Celsius, it doesn't get hotter than that. Okay? This purple line, that is the melting curve for mantle rock, aka peridotite, that green and black rock I passed around before, okay? That's the melting curve for it, okay? So, for us to end up with melted rock, magma, those two must pass each other. But as you can see, under typical conditions, they don't even touch. They barely don't touch in some places, right here in this zone, but they still don't. Therefore, the mantle remains solid. On this axis, we have depth. On this axis, we have temperature. On this axis, we have pressure. There must be some way for those two lines to pass each other. We know it has to happen because we do, in fact, get magma and lava. So what happens? There are three ways that I'm going to be showing you this can happen. Okay? The first way is an increase in temperature. What happens if the temperature of my geothermal gradient increases? What direction is that going to move on this plane? Give me a direction relative to me and you. Are we going to say right? Yes? If we increase the temperature, the geothermal gradient will move right, increasing in temperature along that axis. And then what happens? They pass each other. Boom, bada boom, melted rock. That's the first way. How can we increase that temperature, though? Geologically speaking, what can happen? Not earthquakes, but earthquakes are a byproduct of this process. Tectonics, my friends. Yes, you may. Okay? Tectonic plates moving, crashing, running into each other, generating friction. Okay? Increases temperature in that local area, and you end up with melted rock because the melting point has been passed by the geothermal gradient. You following that? That's the first scenario. The second scenario is you decrease pressure, because what happens as we go up in pressure, I should say as we lower pressure as we go up this graph, okay? Right here, say for example, along the geothermal gradient, what happens if I take that same point on my vertical but increase or decrease its pressure? All of a sudden, I have passed through the melting point of that mantle rock, right? Let's say that I level out at this pressure. I am well within that melting boundary. That is the second scenario. How does this happen? Well, tectonically speaking, yet again, where let's say two oceanic plates are meeting each other, okay? Where new crust is being formed between them. You get something like this. Out here, the crust is nice and thick because it's had lots of time to build. Here at the boundary, though, it's still forming. It is much thinner, which means that, I keep forgetting that all my pens are over here. I don't have a red pen. I'll use an orange pen. All right. That right here, in this zone between the two plates, it has lower pressure because it's closer to the surface than the rest of the mantle around here. Right here, in that zone, the pressure is so low that our pressurized mantle rock is under low enough pressure to now become a melted state. So in this scenario, at divergent plate boundaries, you can get magma. That's the second case, decreasing the pressure. The third one is very interesting. It's a very interesting one. Just add water. It's like pancake mix, right? That's how everyone just makes the pancakes anymore, right? But wait, Professor Hart, that doesn't make any sense. How do you melt something by adding water? Everybody knows that water cools the stuff off, right? We all pretty much understand that, right? You build a campfire, how do you put it out? You put water on it, right? Grease fire, how do you put it out? Don't put water on it, thank you. You dump baking soda on that. I was waiting to see if anyone knew that. Okay, huh? You can cover it, starve it of oxygen. That's true. Baking soda also works. Okay, what else? we use water to generally cool things off. You go for a 10-mile run. I know we do that all the time, don't we? You dump water on yourself to cool off, right? You use water to cool things off. How could Professor Hart possibly be saying you use water to melt stuff? Well, water itself doesn't melt stuff. But here's an interesting chemical fact. I won't take the time to prove it to you chemically because that's not within the bounds of this class. So just take it for granted. When you add water to rock, it has a chemical reaction that lowers the melting point of that rock. It's not melting the rock itself. It is simply adding another chemical to the equation which lowers the melting point of rock. Now what happens if I take my melting point right here, okay, let's say that that's the melting point at that depth, and I add water to it, so now it melts 200 degrees less. All of a sudden my melting point is out here. And what line has it passed?
The solid rock from
The geothermal gradient.
oh yeah.
All of a sudden my melting point is well within the geothermal gradient. And that, my friends, is the third way we can end up with magma. But under what circumstances is water introduced to the mantle which allows this process to happen? I bet you can guess what word I'm going to say next. Tectonics. It comes down to tectonics a lot. So in this example, let's say we've got a continental plate right there and an oceanic plate, which is much thinner but more dense. And what happens in that circumstance? It's going to subduct underneath the continental plate, right? On top of that oceanic plate, I don't have a blue either. I'll just use purple. What's sitting on top of that oceanic plate?
Water.
That's why we call it an oceanic plate, right? There's water on top of it. There's water here, okay? Follow me? I know I'm kind of in the way, but I got to let as many people see as I can. Can you see that okay? All right. So that water is going to have seeped into the top layers of our ocean plate. That water, this rock in the top layers of our ocean plate is containing a lot of water, which gets dragged underneath the continental plate with it. What happens to water when you heat it up? It evaporates. And where does it go? Up. Lower pressure zones. So what actually ends up happening is you get a whole bunch of evaporated water that's trying to make its way back up to the surface. And what's it passing through to get there? You're following along. Yeah, you are following along. What's it passing through? Well, it's passing through the mantle underneath, right? Between itself and the overriding plate. And you know what it's going to do to that mantle rock? That rock is going to what? With the addition of water and the heat it already has, it's going to enter what state? Yes, it's going to melt. Bingo! And you get pockets of melted magma between that subducted oceanic plate and the overriding continental plate. Where's that magma going to go now? Up, because it's less dense than the rock around it. And so we get pockets of magma, aka magma chambers, that make their way up to the surface. And that's what makes our continental, or our coastal volcanic ranges. That's where we get our Andes in South America. That's where we get our Cascade Mountain Range here in North America. Sierra Nevadas. It's where we get all of those coastal mountain ranges that are made by volcanic processes. Why are they near coastlines? Because there's an underneath, there is a subducting oceanic plate taking water underneath the mantle in that zone. This is the third circumstance. Yes?
What about volcanoes in the ocean?
What about volcanoes in the ocean? An excellent question. How thick is the continental or is the oceanic crust? Very thin relative to the continental crust. And when I say thin, I'm talking like 5 to 7 kilometers. Okay? Still very thick for you and me, but significantly thinner than continental. And so it doesn't take that much for a little pocket of magma to chew its way up through the ocean crust. Way less effort than it would take to get through the continental crust, though that does happen, right? Think about Yellowstone and stuff like that. There are these things called hotspots that you're going to learn about on Thursday, the next time we meet, where they are specifically examples like that, where there are pockets of magma that poke their way up through the interior of plates, not just along the edges. But in general, these are the reasons, these are the three circumstances in which magma is made near the surface. Increase temperature, decrease pressure, add water. Yeah?
So, how thick is the continental crust?
Anywhere from 20 to 35 kilometers thick, dude. Like, it really depends on where you are, how old the crust is, how much material is piled up on top of it, and whether or not we're also talking about a mountain range. Think about how thick the Himalayan range is, right? The height of the Himalayas, right, the tallest mountain range in the world, it's twice as deep going underground, right? So it really just depends on where in the continental crust you're talking about. Cool. Right. So now that we know how we make magma, let's talk about what happens to that magma over time. And yes, we have gotten to the part that involves the M&Ms, okay? So let me also, I think I have a stack of these over here. Aha! Everyone also needs one of these papers, okay? So I am handing out papers that I'm going to explain in a minute. So for now, let's talk about this thing that I mentioned earlier, Bowen's reaction series. A while back, in the 19th century, this guy named Bowen decided to conduct some experiments on melted rock to see things like melting rate, solidification rate, all of that. And the results of that were he found evidence that refuted a lot of the things that people previously thought were true, okay? As is what happens with theories and hypotheses all of the time, okay? So before his experiments, everyone always assumed that a volcano always put out the same chemistry of magma at all times. So a volcano that spits out mafic lava always spits out mafic lava and always will. And a volcano that spits out felsic lava always will and always has spat out felsic lava. His experiments proved that wrong because what he found out was as you decrease the temperature, I got everyone a piece of paper, right? Didn't miss anyone? As you decrease the temperature in a magma chamber, you are going to start forming different minerals. The more of those minerals that you form, the less of the ingredients that made those minerals are left. And so what happens is, as you form these minerals, you are changing the chemistry of your magma chamber. AKA, what starts off as a mafic magma chamber will eventually become a felsic one. We're going to learn that right now through this M&M experiment. For those of you that are taking this online, I'm sorry I don't have any M&Ms for you. My camera's not looking. Hello. Thank you. Okay. I don't have any M&Ms for you. I mean, you can run to the store right now, pause the lecture, and go get M&Ms however much you want, right? You can at least indulge in M&Ms with us. Please don't eat them yet. We're going to use them, okay? But I do have the little diagram I'm going to show you here on the screen as we go along with this, all right? Okay, so as we go lower in temperature, we're going to be forming different minerals and changing the overall composition of our magma chamber. So each of you has your magma chamber in front of you, your bowl of M&Ms. I'm going to be showing you chemical compositions for minerals that we form. And you're going to see, as we pull those elements out, you're going to see what the overall composition of your magma chamber change. Look at your magma chamber right now. It's rich in what? It's got a lot of whats. Orange, which correspond to what on our chart? By the way, I have a little code here at the bottom of the sheet. Yeah, orange is silica, silicons. By the way, oxygen is also a vital component of all of these, but you would need so many oxygens it would overfill your bowl. So the oxygens for this experiment are only implied. Okay, all oxygens are implied. Everything else you have in M&M form. Okay, so your oxygens are orange. You also have a lot of irons and magnesiums, right? The greens and the purples. Notice that you also have two brown ones in there. Do you see those brown ones in there? Yeah, they're in there, right? Good. Those represent your rare elements. Right now, the ratio of rare elements to everything else, it's insignificant. You wouldn't even be able to tell they're there without looking for them. Remember that. So let's begin. We have olivine, 2 purples, and an orange. And I know that kind of looks yellow on here, but it's an orange if you were actually looking at the PowerPoint, not on the screen here. The screen's kind of washed out. That's an orange. Yes, and if you ever get lost, you can always consult the chemical equations I've also given you on the sheet here. Okay, the one on the top. Okay, you've got, I've given you here in this example 2 purples, which are magnesium, I believe. Yes, okay, but it can interchange. It can be an iron and a magnesium. Okay, but for this purposes, we're just doing 2 magnesiums, okay, and 1 silicon. Okay, and that's going to go down at the bottom. Why? Because as these crystals are forming in our magma chamber, they're going to sift, filter, fall, thanks to gravity, down to the bottom of our chamber as time goes on. So we've gone through a few million years of making olivines. Having removed those 2 magnesiums from your magma chamber is now more depleted. It is depleted in magnesiums. So now we are going to form pyroxene. 1 iron, 2 silicons. And that is also going to fall down there to the bottom, on top of the olivines. Even more. This is just a general, yeah, as long as they're stacked on top of each other so you can see the order of sequence is what matters here. Okay? It is roughly tied to these temperatures as well. Olivines form at 12,000. Pyroxenes typically form at around 11,000 or 1100, sorry, at 1200 and 1100 degrees Celsius. So that's kind of what I'm tying it into, stacking temperature-wise along the bottom of this magma chamber. Our magma chamber is cooling off during all of this, remember? So at 1200 we formed that, 1100 we formed that. Next up, amphiboles. 5 irons, 3, 6, 8 oxygens, and 2 calciums. Yeah, now we're starting to form larger mineral chains. And how much more depleted in iron are we than before? Much more, huh? The chemistry of our magma chamber, we can no longer say it is ultramafic. We started off with an ultramafic composition because guess what? It's melted a mantle rock. The mantle is ultramafic. We can no longer say that we are in an ultramafic magma chamber. We've lost too many irons and magnesiums now. Okay? It's a mafic magma chamber. Okay? Next up, calcium feldspar. Oh boy, our first light silicate. We have lost so many irons and magnesiums that now we are forming light silicates. We have reached a temperature at which light silicates can form. Okay? 2 silicons, 1 calcium, 2 potassiums. Sorry, not potassiums, aluminums. Now we have lost so many of our irons and magnesiums that we are in an intermediate composition. We are going to form potassium feldspar. 3 silicons, 1 potassium, 1 aluminum. Next up, biotite. Okay, so this is a dark silicate, but it's the last one we're going to see. Okay, so we've got 3 magnesiums, 3 silicons, an aluminum, and a potassium. Biotite mica is very commonly found in felsic rocks, representing the one dark silicate that makes up some small portion of it. Okay? So we are well and truly moving from intermediate into felsic composition. What have we observed? We have gone from an ultramafic magma chamber to a felsic one, simply through the passage of time and the growth of minerals removing the dark silicate material from our composition. What is left is no longer like the original. It has changed. This, my friends, is Bowen's reaction series. Okay? Next up, muscovite mica. 6 silicons, 2 potassiums, and 2 aluminums. While y'all are doing that, I'm just going to put a quick plug out there again. Remember that we do have a geology tutor through the LRC. If you need any tutoring, you can contact the LRC and book a time to meet with her. Or you can contact me, and if it's during normal business hours, I can absolutely work with you. Okay? All right, so that's muscovite mica. Then we've got quartz. 1 silicon. That's the last thing that typically forms in a felsic series. Just the 1 silicon, because quartz is SiO2, the oxygens are implied. Just 1 silicon. All right, what do you have left in your magma chamber? What do we got left over here?
1, 2, 3, 4.
Do you have nearly as much as you had before? No. Now notice how easy is it to see those 2 brown ones. Is the ratio of rare elements to everything else higher than it was when we began? So those rare elements that really don't like bonding with anything have no choice now. They are such a high quantity of whatever is left over that they must bond and form something, and they do. And that, my friends, is where we get our pegmatites, okay? Those rare elements get incorporated into all of the minerals that form at the very end of a magma chamber's life, and that makes pegmatites. And pegmatites are fantastic mining targets. Some of the best mines in the world are built on top of pegmatite deposits. Okay? So through this experience, you have seen how a magma chamber will eventually evolve from ultramafic original composition to expiring in a felsic series. Okay? So what does this mean? A volcano that currently is spitting out felsic material started off at some point being fed by ultramafic material. If we know that you start at point A and you end at point C, you have to pass through point B sometime, right? Yeah? So this is the process. Bowen's reaction series. The sequence in which a magma chamber will change over time based upon whatever is forming inside of it, changing its composition. The sequence of materials that form in a magma chamber as temperature decreases. Okay? Any questions about Bowen's reaction series? Did this make sense? Are you following along okay? Do you need me to explain anything else again? This is the perfect time to ask me again. I'm happy to answer those questions. I wish you would ask questions. No? We're good? Followed that along okay? Yeah? All right, you may eat your M&Ms. All right, we can proceed with the rest. So, magma chambers, that is the general process for magma chamber evolution. There are a few things that can change the ways that this happens, though. Okay? So, as we go through time, our original magma body cools off. You generate all of those minerals around the outside. Chemistry changes as time goes on. You end up with an old magma chamber that is now felsic in composition. But what can happen besides this? Well, here's a few scenarios. As that magma is making its way through the Earth's crust, What is it doing?
Melting off.
Haha, yes. It's not like that magma is saying to the rock above it, excuse me, would you mind moving, right? You know, you're not in a line, right, for Chick-fil-A lunch, right? Can we move the line along, please? There is no polite melted rock, okay? It's chewing and melting its way through the rock above it to get to the surface. And so it's incorporating all of the chemistry from that previous existing rock. We call it the host rock, okay? It's incorporating all of that chemistry into itself. So what happens if I have an ultramafic magma that is chewing its way through felsic rock? The ratio of ultramafic material to felsic material is going to equalize, and maybe I end up with a more mafic mix by the time we're all said and done. Or even, depending on how much felsic material it went through, it could even end up as an intermediate magma by the time it reaches near the surface. Okay? So that's one way that you can interrupt Bowen's reaction series. The other way is, what happens if I have an old magma chamber far along, maybe it's in its intermediate or felsic phase, but then a brand new ultramafic magma chamber rises underneath of it, pierces through it, and they mix. The old magma chamber and the new magma chamber mix their magmas, and Bowen's reaction series starts all over again. So there are things that can interrupt the typical cycle of the series, but they're all things that we can observe. They're all things that we can see happen in the geological record after the fact. They're all things we can comprehend. Bowen's reaction series, though, typically will progress as the way that it did in our exercise just now. All right, let's talk about partial melting for a second here. Partial melting is when you add just enough heat to cause something to melt, but other things not to. We already talked about that with porphyritic igneous rocks. Okay? Here's an example video right here. Okay? So in this example video, we have 3 materials. The first one is going to be linseed oil right here, currently in a frozen state. Then water, currently in a frozen state. Then chocolate, currently in a frozen state. We're going to increase the temperature slowly. Starting at negative 25 degrees Celsius, we're going to start increasing the temperature. The oil starts melting almost immediately, right? Doesn't take much to melt that. Let's call that the quartz in our granite. Melts pretty easy, forms last. We increase the temperature to 0 degrees Celsius. Guess what? That's the temperature at which ice melts. That's more like our feldspar in our granite. Okay? If I were to keep increasing the temperature even more than that, all of a sudden, we're going to get to a point where, say, my hornblende amphibole starts to melt. But it's the last thing that starts to melt. Okay? I could have left it at 0 degrees Celsius, and these two would have been total puddles while chocolate stayed solid. This is partial melting. Okay? Let's talk about the igneous bodies that form as a part of this process. Okay? So we characterize igneous bodies by their behavior and their shape. These magma chambers that I was talking about before, I'm going to get a little bit more detail on those now. Okay? So their shape can either be massive or tabular. Massive is just kind of a big blob. Tabular is a straight direction of intrusion. Okay? Talk about each of those in a second. And then there's the orientation of the host rock, discordant or concordant. Discordant means that it cuts through the previous host rock. Let's say that I've got layers of igneous rock, or of sedimentary rock. Okay, so let's say I've got multiple layers of sedimentary rock that existed there before, and then I get a discordant igneous intrusion, like that. That means that it cuts perpendicular to the host rock. Okay? This is very important. If I ever ask you, and hint, hint, I will at some point or another, to describe the difference between a discordant and concordant igneous intrusion, you got to remember this terminology. Discordant is perpendicular to the host rock. Concordant is parallel to the host rock, perhaps cutting between 2 layers. It's easier to go that way, maybe. Okay? Why am I putting so much emphasis on this? Because far too many people default to horizontal and vertical. Would horizontal and vertical work in this circumstance the same way as parallel and perpendicular? No, because those have no frame of reference to the previous rock, horizontal and vertical, I mean. If the previous layers of rock were tilted 90 degrees by tectonics, so what was originally deposited horizontally is now like this because of tectonic activity. Which one is the discordant and which one is the concordant? If you're going in terms of verticality, you would say this one is the discordant one because it's vertical. That's why it doesn't work. In this case, it's parallel. But a discordant layer is always going to be perpendicular to the host rock. Okay? Hope that made sense. So now I'll give you examples of these. For tabular bodies, a dike is what we call a discordant tabular body. Okay? So an igneous dike is a layer of igneous rock or magma when it pushed its way in there. Okay? It was melted rock that shoved its way perpendicular to the original layers of host rock and then solidified there, crystallized. Okay? So it's discordant. A sill is a concordant layer, a tabular body of igneous rock. So instead of pushing its way perpendicularly through the layers of host rock, it went parallel to them, usually between two of the layers. Okay? So that's a dike and a sill. Discordant and concordant tabular bodies of igneous rock. That's a dike, and that's a sill. Okay? Then you've got your massive bodies of igneous rock. Okay? So the first one is a batholith, which it's impossible to say that without sounding like you have a lisp. Batholith. Okay? Batholith. Yeah, it sounds like you're saying basilisk with a lisp, right? It's a batholith. Okay. So these have more than 100 kilometers of square area, okay, on their top. These often will make a mountain or multiple mountains depending on the size of the batholith in question. Okay? Anything smaller than 100 kilometers square at the top, we call that a stalk. So batholiths, big, massive, igneous bodies. Stalks, smaller ones, massive, igneous bodies. Okay? And whenever you have an offshoot, like right here in this example, here's our stalk, and you can see several dikes and sills branched off of it and started pushing magma out of the stalk and over here into a little side pocket. And that side pocket pushed the layers of rock above it upward. That's called a laccolith. Okay, so batholiths are the big ones. Stalks are the smaller ones. And laccoliths are kind of like a side chamber off to the side of the original body. Okay? And then the last thing I want to mention is mineral resources. So we get a lot of very important mineral resources out of these igneous rocks, in particular those pegmatites. The pegmatites are the places that mining companies love to target because you can get stuff like lithium, cesium, uranium, those rare earth elements I talked about before that we need they're vital for our electronics infrastructure. All of those things are found aplenty in pegmatites, which makes them fantastic mining targets. Okay? You can also find a lot of gold in those. The gold mine I worked at in Nevada, my job was essentially to Sherlock Holmes old magma chambers. Okay, what do I mean by that? The magma chambers that we were looking at have,
Like go discover everything, like find everything.
I mean, yes. The magma chambers we were looking at cooled off in the Jurassic period. They were Jurassic era magma chambers. A lot of them were anyway. But the pegmatites that formed at the end of those magma chambers were rich in gold. In the millions of years since then, the gold was dissolved and transported away by groundwater movement. My job was to drill holes in the ground, or to, I should say, tell a drilling rig where to drill holes in the ground. I didn't do the actual drilling. to drill holes in the ground and bring up samples that I could analyze for gold content. And if I did that across an area, I would find where the passage of gold was by finding the trace elements of gold as it left that pegmatite millions of years ago. And so I'm essentially following the track underground of wherever that gold went until I find where it stopped, where the groundwater took it and deposited it. And at that location, we build a new pit mine. Okay? It's a very long-term operation. From finding the location to actually making money off of the pit would often take 5 to 20 years, depending on the size of the pit and how diffused the gold was through the rock. But that was the job, and it was fun, right? Literally, playing detective, tracking the passage of gold 500 to 1,000 feet underground 100 million years ago, right? Okay, so this is called a hydrothermal solution is what it's called when the mineral gets dissolved in the water and carried away, okay? So that was a hydrothermal deposit that I was looking for, okay? Any questions about anything today? Yes?
So how did you know where the gold was? Like whenever you were drilling it after it's all like mixed up from, like you're getting drilled.
Oh, you make a core, okay? So a lot of the drills, like in the oil industry and in the mining industry, they're hollow on the inside. And so they'll chew a hole in the ground, yeah, but there is a column of rock that survives and then gets passed up through the middle of the drill. And it gets brought back up through the middle of the drill tube, and we can extract it from the drill tube, and we know exactly what depth it was at because we know how many feet of our drill have gone underground. Okay? And so I know I have boxes of core from depths that I know where they're at, and I can analyze the metallurgical content of each of those cores and figure out at which depth the highest concentration of gold is, and then say at that depth it went that way. And then we can just follow the path. The party started already. Okay, what else? Great question. Nothing? Okay, well, if there are no more questions, we can move into lab time. We have an hour until class is over.